All right, well, thanks for coming. Let me introduce to you Eric Frater. He's been a PhD student here for some number of years. I don't know how many.
5.
5 years. Working in different areas of optical alignment, optical fabrication, optical testing. He's going to present his dissertation work, which is very specific on the use of computer-generated holograms for optical alignment. Eric has contributed to our group and to university projects in a number of ways. The most important for us is we had the system that we needed to deliver the prime focus corrector for the Hobby Eberly telescope, which by the time Eric worked on it, it was late and we had all kinds of technical problems, and Eric was really part of the group finishing this, providing the solution. And I remember at the time, Eric really loved it because he got hands-on to do careful things. He got to work with Brian, and if you ever work with Brian, you're really lucky because Brian's really fun to work with. And then it went on, and it went on, and Eric was asking me, when do I get to do my dissertation? When do I get to do my dissertation? I said, just stick with it, get it done, we'll get you there. And he did. He stuck with it. Those guys finished this, did a great job. You'll hear a little bit of a summary of it from Eric. And then he went on to do what is really fundamentally groundbreaking independent research that he's going to present here. So I think this was, from my point of view as the professor, I think this was fantastic for Eric because he got to see, really have firsthand experience with the difficulties of practical aspects of things, and then go on and do some theory and push the envelope, see what can be done. So with that, he'll tell you about the cool things that he did. Thank you again for coming, and I'll give the floor to Eric.
Thank you for the introduction. And Jim's my advisor, and he's been great throughout the whole process. So this is the oral defense of my dissertation, and the title is Optical Alignment with CGH Phase References. As Jim noted, a CGH is a computer-generated hologram, and if you haven't heard of one of those, or if you need a little refresher, we're going to talk a little bit about what that is, so that you're not totally in the dark. So first is just kind of a fun thing. I'm going to give a quick personal background. I came from Wisconsin, which is cheese land. That motivated some of the snacks. And there's a little peninsula here, and it juts out into a lake, and it's surrounded by sky blue water. And then I came to Tucson, which is kind of a big change. But I have a lot of fun out here too, and I like all of these cool activities, including sort of type 2 fun, going on really long walks. And I also like making stuff. Jim mentioned, I really like doing HET because I got to make something come to life. And that's true also in my personal life. With Brian, we came up with this cool design, and then it came to life, which is a lot of fun. So before I get into the new things about optical alignment that we're going to get, that the research got into, I want to talk about what optical alignment is inherently, so we understand kind of what the goal is. So first of all, in optical alignment, you typically assign some datum. So there's some object that you align everything to. If we have this set of lenses, A, B, C, and then a focal plane, D, then we want to choose something we align everything else to so that we're not just putting it somewhere arbitrarily in space. So we're going to align all the lenses and the focal plane to C here. And then, once you have that assigned, you make some reference frames so you can give labels to all the different degrees of freedom that you use to align it. So A, this is an optical element, and it has an axis of symmetry. And so this is going to have relevant alignments in X and Y translation, Z translation also. It sets the air gap between A and B, for example. And also its tip and tilt. And so the same is true for B. And D, since it's just a plane, it's mostly just tilt that matters there. But once you have all these degrees of freedom assigned, you need to somehow constrain them all. So you can do that by a mechanical constraint. You can build a structure that all of these lenses drop into where they fall into place to some accuracy. And so how well you make your mechanics is how good the optics are. You can also use an extrinsic measurement, and that refers to using some other instrument whether it's mechanical or optical, to test where the objects are and then actually actively adjust them to put them in place. And then you can also use intrinsic compensation. If you have a really simple system like just a detector and a single lens, you might just look at how well it's focusing light and move the two and use the system performance to align it. So the last example, we were kind of assuming that's all simple spherical lenses, and those were elements. Now, if you have a single spherical surface, you can roll it around its center of curvature, and because it's symmetric in that sense, it really only has 3 degrees of freedom. You can call it tilt or you can call it decenter, but that's rolling it, and then there's the other degree of freedom, which would just be where that center curvature is along the axis of the system. Now, if we have an axisymmetric aspheric surface, then in profile, it might have this wiggle to it. So if we have this strange optic, it at least has an axis of symmetry, and so this single surface now actually has 5 degrees of freedom. It acts like a whole optical element in itself. And if you go one step further and make something that varies about the z-axis, then really the surface profile is defined in its own local coordinate system. And in that case, you also have the rotation clocking about its z-axis, which is really all the possible degrees of freedom matter in that case. So, hate to give more of an egg in the face to this project, but we're going to use the Hubble Space Telescope as an example of why alignment matters. So if you have advanced aspheric surfaces, then you also need some advanced alignment methods, or a great deal of care and sometimes new methods to align them. And if you have a poor alignment, you'll have poor performance. And there's a lot of ways to get it wrong versus kind of one way to get it right in some small range in what's tolerable. So if you have an imaging system, what could go wrong? You might have a blurry image, you might have a distorted image, you might have magnification error, all kinds of things can go wrong there. And in some of the applications we're going to talk about, which is surface metrology, where we're testing the shape of a mirror using an optical system, separate system. If that separate system that serves as our reference for is this mirror the right shape, if something's misaligned there, we're going to make the wrong mirror. And so that happened with Hubble. They had a misaligned instrument within their test, and they made the wrong mirror, which is really unfortunate. So you're likely to fail if you don't align things right, and I'd like to help us all avoid that. So here's some conventional alignment techniques. So you know where we're starting with, or where we've been for a while, really. So one of these is the alignment telescope. So it's simply a telescope in one sense, because you can see things with it, so you can image different objects along its line of sight. And this barrel, the telescope, is often used as a kind of reference for where it's looking. And an autocollimator can test the angle of flat surfaces. I forgot to mention this, but actually the alignment telescope can see the orientation of optical surfaces because it has a source of light within it. So that's a pretty clever, versatile instrument. It works well with spherical surfaces, not so well with aspheres. So interferometer is a little bit more adaptable, so we can make tests that do test aspheres. And actually, my application is going to use an interferometer in a different kind of way than just testing the surface and adjusting it to vary the response. I give an example of what an interference pattern looks like from one of these instruments here. So this is an interferometer set of fringes, actually from HET. And these lines going like that, which is the dominant thing you see there, that's a characteristic called tilt, so that indicates alignment. This is a collimation test, and it's basically indicating a well-collimated system there. The star test is an intrinsic measurement where, let's say if you have a new telescope and you look on the sky, does the star make a sharp image? That's what you're testing there. Mechanical diagnoses include things as simple as what you use in the machine shop, calipers, micrometers, things of that nature. And we also sometimes make a nice lens centering setup where we rotate everything and about some bearing axis, and we align all the optics to the bearing. So here's an indicator, and this would move in and out to indicate whether something is aligned with the bearing or not. Some more modern additions, would be CMMs, coordinate measuring machines. which can measure things in 3D through some given range. And a laser tracker is pretty cool. It's got a little robotic head, and it uses a laser, simulating it here, to shoot in the middle of this retroreflector, and it tracks it around when it moves. So it can tell where that ball is in 3D space. And we've used those extensively, including in the HET project to do alignment. Now, the computer-generated hologram has been the elephant in the room here since I gave it in the title. And I'd like to tell you what it is so we understand what we're dealing with here. So this is a diffractive optical element. It's not like a lens, which is refractive, which has a smooth shape to bend light. The CGH actually divides up light, and some portion of the beam that you illuminate it with, it can shape in a way that is very versatile. So I'm going to describe what I mean by shaping here and what I'm referring to as phase. So continuing with what it is fundamentally, there's actually one sitting in the room here if you want to look at it. It's interruptions in across the beam profile, which can either be in the form of blocking and passing light, or you can have little steps in the glass that allow the light to go a different length through the glass. And so that's what allows it to do what it does. A few of the things you can make a CGH do are focus and distort light. And so that's again talking about the shape of it. And let's now make reference to the figure here. We have these wave fronts I've referred to. Here, they're in the shape of planes, and past the CGH, they're in the shape of spheres. All the light in this wavefront left the source at the same time. It's all in phase in that sense. And so once we've shaped it into a plane, let's say that's our control, and we want the incident light to be like this. Then we design the CGH so that it shapes it into a sphere with a given radius of curvature out here. That radius of curvature determines how far away it's then going to converge on its center of curvature to focus. So the shape of a wavefront determines how it travels through space, and in this case the beam gets smaller down to a nice little focus. So that's one function to consider, but extending this, since I've been talking about spheres and aspheres, we can shape this wavefront into any shape. So, I mean, just about. There's some limitations on that, but we can make it pretty much any aspheric shape we want using this element. And the wavefronts are defined as surfaces of constant phase. And so with that, I'll connect this to the title. The CGH serves as a reference for phase. Now, this is a picture actually of the CGH that's sitting in the room, and this would be a Fresnel zone plate. So we've got these rings going around that are masked in chrome. And we can do other things other than the shaping of the wave. We can make a target here that we can image with the alignment telescope, for example, and we can make a beam stop. And so this is mentioned to point out the versatility of these. We can make different patterns for other purposes in the test or in the alignment. Now, CGHs are used extensively in optical testing, and I'd like to introduce the CGH used in an interferometer. And an interferometer, just since we haven't mentioned what that is yet, it's an instrument that will divide a beam of light into a couple different beams, and we're going to end up comparing the shape of wavefronts in the different beams. And we can use it for metrology to test a surface shape. The way we do that is, first of all, we have the illuminating beam here. This is kind of a simplistic, conceptual version of the interferometer. So the illuminating beam comes in here, and we put a lens here to focus the light right here. And so with this thin reference surface that I have here, it'll have a computer-generated hologram on the opposite side. But for our reference beam, ignore the presence of the CGH. That it basically doesn't interact with that. The reference beam propagates out to this surface as a spherical wave from that point source and reflects straight back because it's aligned to that. We're assuming it's aligned. And so it comes back just the way it came, same shape, and goes back through here, and it eventually comes to a detector over here. So the other side of this, or the other branch of the interferometer, is some of the light goes through this surface. And so that's the blue profile I showed here. That's the aspheric test wavefront. it got to be aspheric. It got to be a surface or a wavefront shape that is complementary to the test surface by diffraction of the CGH. And that diffraction can actually work in reverse as well. So it can go through, reflect off of that, and be shaped to in the opposite sense, or it can even pass without interacting. Because again, the CGH is only interacting with some portion of the light. So then, after it adopts that correct shape and comes back, it matches the reference surface in shape. And that matching of the shapes is important for our wavefront comparison. So this is, again, a view of that interference pattern, an example from HET. And what I wanted to point out here is that these ripples, these fringes, can come from different kinds of errors. One to be a misalignment, and one to be a surface shape error. This really high frequency wiggle of the fringes, that's due to surface error. And so discriminating between the two can be kind of hard. And that's something that motivates us to have other means to align things so we understand what's a misalignment and what's a surface error. So here's one example. It's a different kind of interferometer, but basically light needs to come back to this focus to make a null. So we have one pattern that tests our aspheric shape. That's the inner pattern on the CGH. So it shapes the wavefront to adopt the same shape as this to make a good match there. There's an outer pattern also on the CGH for the sake of locating where this optic is, because that's our reference, relative to the focus in the test. So we have this annular zone here that is for the sake of aligning the CGH to the interferometer. Now, that's how we align the CGH. You can also use these to align the test surface. And here I'm giving a cartoon of something similar to what my research is going to be concerned with. So in this case, we might want to know exactly where the test surface is relative to the CGH. So if the CGH makes a little focus that will go to the center of curvature of this little alignment feature and retroreflect, then we can observe an interference there to say, it's aligned to these features, and then observe what we get as a response from the test surface to make that separate measurement. And so both of these are examples of an independent means of checking the alignment and checking the test result so that you don't have it too convoluted. So those are examples in testing. Now, this is an example that's sheerly for the sake of alignment. In this example, we have a computer-generated hologram mounted in a fixture in the center of these mirrors. And this will be applied to the HET wide field corrector alignment. So this shows a cartoon of multiple mirrors with these little CGHs in them. Now, in this case, we illuminate the first CGH, and this serves as the datum in the alignment. And it makes two foci, one close to it and one far away, where we have a camera to image it. So this is the first step. You place just this one in here, and you observe where that spot is in the camera's field of view. And the two spots define an alignment axis. Once we place a second CGH in here, it's going to serve, we can actually block this light, by the way, so in the dotted lines, that's showing where the reference spot was, but we can block that out. And now, this will be imaged by the CGH to this camera, and if we have this off-center, it'll move that spot, and so the difference in where those spots fall will diagnose a decenter misalignment. And you can add really as many as you want, and co-align everything to the first one. So with that, I'm going to move into this system, the Hobby-Everly Telescope Wide Field Corrector Alignment, and I'm going to talk about the system itself and talk about the alignment and also the results of that. The results are exciting. Here's an overview, a little bit less of a cartoon or a layout of the system. There's 4 mirrors. And one of the notable things here is it's large. M3, which is right here, is 1.2 meters in diameter. And so it's a 1 meter class system, we refer to it as. And the alignment tolerances are kind of absurd. 20 microns is the alignment tolerance for this mirror in X, Y, or Z relative to this mirror. And that refers to the spacing between the vertices that don't actually exist. So there's no way to directly measure it. You have to make separate references, and you have to measure this surface and calculate where the vertex is, and it's very subtle. So M2 and M3 had a tilt tolerance of 49 microradians. So if you were to take a little shim that's 2/1000 thick and put it on one side of this guy, or 2/1000 of an inch, or 50 microns, you would throw that out of tolerance. So it's very, very sensitive. And all the mirrors are very aspheric. That's part of what makes all that difficult. So going back now to that CGH co-alignment I just showed you, and showing parametrically how it behaves. So here delta B is a misalignment at second CGH. That's something we wanted to detect, because that's how we get feedback on where the mirrors are in centration. So these are ZB and ZB prime. Those are the distances from that focus provided by the first CGH to the focal plane where we observe all of the foci. That defines this parameter of the magnification. That's negative, so I want to mention that value is in general negative for our setup, because the sensitivity depends on 1 minus MB. And basically, MB is proportional to ZB prime, so the farther this CGH is away from there, the more sensitive we are. We can determine a smaller misalignment. The uncertainties based on Laura Coyle's work when she did this all in the lab and scaling that to this system are expected to be tiny. It's basically 0.4 microns is how well you can locate M5 to M4, and going up to 3 microns. And so in our implementation, that took up a tiny portion of the error budget. Actually making the references and their accuracy was a lot more of a challenge. So that was not a limiting factor, and worked great in practice. So we did have a instability in some of the degrees of freedom of the references. So also in that sense, the references were the issue in this implementation. And we had to use another form of using a CGH as a phase reference to align these mirrors, where we had these separate subsystem tests, because we eventually did a full system test, but we had these independent tests to verify the alignment of M2 relative to M3, M4 relative to M5, and we also had this test aligned to that test. So pulling this all together, we had an alignment uncertainty for the absolute locations of these, the absolute values of the tilts, and that would be relative to the rest of the structure. They were relatively high, but for one mirror relative to the other, it was certain enough to be less concerning, let's say, and we expected that it wasn't going to cause a problem in the analysis that was done to support going this route. And in the case of the M4, M5 test, similarly, there was 1 degree of freedom that was a little bit out, but also this alignment is different, or these alignment errors that I'm referring to are a different kind of error because there's a different method used to align it. That's part of what allowed us to justify going this route. So in the end, we had these final results, and the only results that are so these are the expectation values in this column, and this is the total uncertainty over here. And so there were some concerning ones, which were M3 and M2 tilts, but their relative tilts, when we did this test a couple times, were within that bound of basically we could pretty repeatably show that M2 is fairly well aligned to M3. And everything else was pretty well set. And so we were able to justify shipping it, which was really my entire goal. So this is the transmitted wavefront for the system test. This is a pretty cool view. Right now, we have this thing tilted at 35 degrees, and that's the orientation it works in the telescope. So we simulated how the structure would bend, we actually tested how the structure would bend directly as it was used in the telescope, and then performed the test and got a result that passed our specification. So that was what we did in the lab, and then outside of the lab, we have our customer, which I have to acknowledge for actually generating this data. they installed the corrector in the telescope, and across its field of view, and that was a big concern, is they show these gray areas, which are possible performance areas for what we had measured. That didn't come true. Instead, they're getting basically right around the spec for how well the corrector is able to image distant galaxies and discover things about dark energy. So this is a time-varying plot, by the way. So over time, you can see that the contribution from the atmosphere is much greater than in black what our corrector contributes. So it's seeing limited, and that's good. Now I want to talk about a surface test for the Tokyo Atacama Observatory secondary mirror. And this is a convex hyperboloid that we had to do a interferometer test to make sure it was the right shape. And so this mirror is still here actually in the basement. This test has a computer-generated hologram here, which is remote from the reference surface and test surface, which are over here. So this is what we refer to as a Fizeau cavity. The interference of light that we observe over here will be between light that reflects from this surface and from the secondary mirror surface. The special thing about this interferometer is it uses a projection lens to align this kind of an image of the CGH to the Fizeau cavity. And so we want to know exactly where that CGH is here because it's supposed to accommodate an aspheric surface. And we need to align all those things to understand our test results. So I would like to illustrate what happens when it's not aligned. Here's kind of a cartoon of the same interferometer, CGH, projection lens, and then the Fizeau cavity here.
Let me ask you, why did you go to this unconventional test to test the secondary and not use something more conventional?
There was another test, so this is actually a redundant test. The other test was a swing arm profilometer, and the goal of this test was to partially to help calibrate the results you get from the swing arm. That collects data a lot more efficiently during fabrication, but to get the low order errors right, this test has big strength. So the conic constant is one of the parameters for a conic section. This is a hyperboloid, and we were looking to get results from this test for that, and also they had a structure function spec, so high order errors we wanted to check, and an interferometer observes those very well and gives the customer a lot of assurance. So that's why we did this. So here we have the aspheric wavefront, which should accommodate the aspheric portion of the mirror surface. This test tested a lot of different parts of the mirror and then combined all the data. So if we have a misalignment between these two and we don't know it, that's this case here, then when the light reflects off of here, that lack of a match between these two will cause an optical path difference that we measured in the form of those little wiggly fringes that I showed before. And that can be construed as a measurement error, or well, it's measurement error that would be construed as a surface figure error. So if we didn't know there's a misalignment, we would say, aha, we need to polish that glass. And then we'd remove glass and actually create an error where there wasn't one. So in this case, we have everything aligned, and you don't have the measurement error. And so we want to align that projection. That's the point I'm trying to make from that. So the current method of doing this actually uses the CGH in a kind of different sense, where since it's a printed pattern, we've left little holes in the chrome in certain spots, and that makes little incoherent point sources. So this is the part of the actual layout of the interferometer. It has a fold mirror, so this is just a flat mirror. But the CGH is projected by this lens here to the reference surface. So outside of the holographic portion of the CGH, there's these little point sources, and they get imaged just like any of the light by the projection lens to this area down here. But it's outside of the test, and so we have these little CCDs to detect it, where it is. And we've separately measured where the CCDs are relative to this point. And so through a complicated set of coordinate measurements, we can understand, that's where the projected wavefront is relative to the reference surface, and then align it to the test surface. So because I think partially because of what those spots look like when you do this, they're kind of large spots. You have some irregularity in the pattern that they describe. From our optical model, we expect this definite pattern. Okay, these will be at these XY locations. But when we made the measurement, they had an irregularity from that pattern. So this isn't alignment residual, this is actually the irregularity where the spots fell on the cameras. That was at about 50 microns. So that's a third of the tolerance we had assigned for this. That's part of why we have this large tolerance, because there was that factor, and then there's a lot of other factors that make it difficult to make this alignment in that way. And so the rest of the presentation is going to address how we can improve on that. And I'm going to introduce now what these phased fiducials are. This is the kind of interesting thing that we're going to treat as a general way to align stuff, or at least these interferometer tests, and show the design and performance in the case where we have an interferometer like the one that I just described, this CGH Phase interferometer, and then another case where there's a CGH that directly basically shapes the wave to accommodate a optic under test that directly follows it. And then I'll talk a little bit about what causes the errors as we go on. So I passed this around the room. Maybe some of you had the chance to look at it. The alignment features are little dimples in the glass. So in this case, we have a 2-inch piece of glass, and this is one that I actually made. So it's nice to have an example when we're talking about it. And I define it in general as a feature that's on a parent optic that has a curvature that's distinct from the parent optic. And that fact that it's distinct is what allows it to be used as kind of an independent reference for the alignment. If it was the same shape, then it would look like the rest of the optic. So the way we're going to diagnose these and use them for alignment is with interference. And so this is an image of what's to come in the demonstrations of this, where you have an interference pattern from the parent optic, and simultaneously these little subaperture areas have a different interference pattern. You can see the density of these fringes is quite different. We're zooming in here, and you can see this tilt. And that's the signature that'll indicate how they're aligned to the projected wavefront. So I want to show some of the parametric treatment of this now. In general, you could make a unit under test, that's what UUT stands for, that has any curvature, and then make these little dimples in it which depart from that curvature. So the curvature difference, CF, that's going to be an important parameter for us in the design of these. And it's the difference between 1 divided by the radius of the fiducial surface and 1 over the radius of the test surface. So here's the curvature, or I'm sorry, here's the departure from the parent optic drawn in blue for the surface. And I call it surface OPD, and essentially if you didn't have, since we're comparing wavefronts, this is in the test branch, it'll influence OPD with this characteristic. So you might see this profile if you measured it. But if we use a CGH, that also influences the optical path difference, and if the two match, then you get 0 OPD that you measured. But if we have this shear between them, this misalignment, and that's what we're trying to detect, then you see a difference that looks like this. So here's this slant here, and then here's the parent optic that you're still getting a null from. So then you see these tilt fringes. That indicates that OPD profile. And the alignment sensitivity scales with the curvature difference and the diameter of it, because this is the peak to valley, the full range that it departs. And if you get bigger than that, same slope just continues out, so you get bigger difference, and it's easier to measure. So what I did here is take something like the TAO test, this CGH corrected Phase interferometer, and break it down into a set of parameters using a first order model. And what we're going to show is that this simple treatment of it up here, turning this into this, is going to be proven to be valid in designing these features for the sake of alignment. So in red I have, this is the first order model of the interferometer, and in green this is the path that the light travels when it bounces off of the little subaperture phase fiducial. And so the focus, there's an intermediary focus, there's a source point here, and that's imaged by the condenser lens near the projection lens, but that becomes a different distance, ZF, as a function of how much the curvature departs. So that moves farther away the more, or the bigger CF is. So here's the test parameters, and you don't have to concentrate on exactly what every one of those numbers are, but from relating this to that, you get a set of parameters that you can use for designing these features. So an interesting thing I'd like to point out is that if you want to have this measurement give you an idea of where the alignment is within a large range, and you also want it to be very, very sensitive and low noise, you can't really get both, because there's an inherent trade-off between those two. And this is actually gotten relatively simply from this analysis. And one of the assumptions that it's based on, which matches what I did in measurements, is that you need a certain number of samples when you're measuring these fringes. They can only get so dense before you can't resolve them anymore, and then you can't tell how much the misalignment is. So the sampling is one of the limitations, and the other thing is the higher the curvature departs, the denser they get for the same misalignment. So you have an inverse relationship of what's the maximum amount of misalignment you could have and still measure it with respect to the curvature difference, and then it's directly proportional to the curvature difference here. So here's curvature difference, sensitivity goes up linearly and like 1 over the curvature difference. And this is kind of nice normalized expression for it. So lambda over 2 times those same factors up there relates how much shear corresponds to 1 wave of OPD. So I put the design space for the TAO interferometer into a graphical form where every one of these curves represents a curve of constant sensitivity you're getting for making an alignment with the features. So here's the curvature difference, and here's the diameter of the feature. I limited here at 1 inch, because you probably don't want to take up too much of the clear aperture, and already you have quite a few samples across it, so diminishing returns, I guess, from going too high there. And then there's cutoffs where you can't have it too small because you need several pixels across it, maybe you say 11, something like that, to get a decent, image of the, to get a good image of the response that you're looking at. And so there's another cutoff, which is the aberration threshold. So we're making a projection, just like the projector is. And if it has a lot of aberration, in our case, it's like it's a compensated projection, so it can have a lot of aberration. We can compensate that with CGH, but there's a certain point where you actually can't, because you want to have, well, there's a ray crossing at the CGH in the model, and you can't really do that. So that's what those cutoffs are. What I've found is the optimum possibility, given all the parameters from TAO, is to have a 38 micron shear correspond to 1 wave of OPD. And if our noise level is 1/20th of a wave, then, it's reasonable for a phase shifting interferometer, then we can get a standard deviation of our results somewhere around 1.9 microns. So that's a pretty low noise level. And I'll talk later about how some other things might be more limiting to us anyway. And the dynamic range, to give you an idea of how far things could be out of alignment, could be 0.23 to 0.75 millimeters for the same parameters. And so that's certainly a useful dynamic range. By other means, we could align it within that range and then work from there. Now, a different kind of test that I mentioned before is where you have the CGH directly before the unit under test. There's no projection lens or anything. And so in this case, you have commercial piezointerferometer optics. This would be your reference surface for the planar beam. So there's a transmission flat. And then the CGH does all the beam shaping to accommodate the unit under test. So again, I've made a first order model here to show this, or to treat this in a general form, and also treat this situation where you make the separate alignment references in a general form. And what this shows is a matched obscuration of in red is the test beam, and there's a matched obscuration, a proportion of the clear aperture of the CGH for making a beam that accommodates the alignment feature here. So we could make this really large and have it focus on that, but the light would just get thrown away. So this is the most efficient way to do it, and that's one of the design constraints for the fiducials. The other thing we're doing is considering the possibility of just putting half-inch balls outside of the unit under test, but directly connected to it. And the value of that is that those features are directly measurable with a laser tracker. So in that case, you have the optical reference, it actually is the mechanical reference. So there's kind of an attraction to that idea, and we try that out too in these designs. So these are a similar thing where you have a concave optic, the other one was convex, and in these two I have the same size CGH, the same proportions of the CGH used for adapting to these different features, but the distance grows and we have a larger optic. And so we want to see how far we can press these methods in terms of having a large optic that's far away, because we test large optics here. So one thing that limits these methods is if you use a ball as a reference, the ball's surface is very close to the geometric focus. So let's talk about geometric versus real focus. Here's a profile of a Gaussian beam footprint. So here would be the diffracted beam, and it doesn't come to a perfect focus because we can't make perfectly sharp images of things. The larger you make this cone angle, the tighter you can make this focus, but we don't necessarily have that ability when it's really far away and we're not trying to have a 5-foot CGH. It's hard to make those. So in this case, we have the focus very close to, or I'm sorry, the center of the ball very close to, where the beam reflects from the ball is very close to the focus. And that poses a problem because once you get into here, we were assuming we had a tiny radius of curvature of this wavefront if we treated it geometrically. And that's what the first order theory does. But in fact, the beam near the focus flattens out. And so our simple theories don't work when you get to that point, and it'd be a little bit more complicated to design these features there. So now we want to compare these. So in the case of the fiducials, they have the advantage of obscuring a relatively small part of the CGH, and how much of that space we use up is a pretty big commodity in optical testing. So they have that advantage. They have one disadvantage, which is they're on the optics. So if that's actually the optic you care about, you have to sacrifice some area of your aperture for this alignment. Now, in the case of the balls, they obscure more, but in general, they have a better dynamic range when they're close in. However, that breaks down when they're far away. There's this concept called beam walk-off, where basically if I was shining a flashlight at a mirror through a hole and I was trying to see my flashlight beam, there's only so much I can move the mirror before I wouldn't see it anymore. The farther the mirror gets away, the more it's apt to throw that beam outside of the hole, because for the same angle of misalignment, it throws it farther. And so when you have, sorry, I should go back to that one. So when you have the optic farther and farther away, you move it the same amount and it'll throw the beam out of the aperture faster. So that's more of a problem for the ball references, and they become pretty, almost a lot less useful, let's say, for that limitation when the optic gets far away. Additionally, well, I just want to note that the sensitivities for all these, I kept that constant, so we're comparing apples to apples here in that sense. And limiting all of this is as it gets farther away, you get lower and lower sensitivity. So it'd be hard for us to do this in a really big optical test of one of our mirrors that doesn't have the reference optic anywhere near the mirror, because as the CGH gets farther and farther away, you lose a lot of sensitivity, so you lose the value of it. And then this is just showing what we discussed before, where in general, fiducials are better for not obscuring things, but the dynamic range for the ball is a little better. And they serve as mechanical references, so they still have that advantage. Now, I'm going to talk about the measurements of it. I've shown a couple images of the measurements I made, but we're going to get into it more specifically now. And first of all, I'll describe what these experiments were and what they were testing. And that'll be similar to what I just described parametrically. They're basically testing that theory. I'm going to describe my experimental apparatus, which is a similar instrument to the TAO mirror test. And we'll talk about how we made them, that is the little alignment features, and the experimental results, and then draw some conclusions about these. So there's two different kinds of experiment I did. One where there was just one alignment feature on the glass, and then a set of experiments where there were two alignment features on the glass. And with these two different kinds of setups, I could test different things. In the first case, I could measure a translation of the CGH. And the reason I translated the CGH is because if I translate that and it moves in tilt, it's not going to make the tilt fringes change. It's just, it acts like a thin lens. And if you tilt a thin lens, it doesn't really tilt the beam so much. So that's why I chose to move that. But it does effectively shear the projection of it. So that was a nice controlled way to vary that. And as I changed that location of the CGH, I could determine what is the sensitivity, what's the dynamic range, and then what's the noise of this, and did it match my expectations? And in the case of having two fiducials, I have the opportunity to measure a couple other things. First, I repeated the experiment of moving the CGH in the transverse direction to get the sensitivities calibrated. So then I could tell this amount of change in OPD corresponds to this amount of movement of the projection of the CGH relative to the test optic. And with that calibrated, I could then move the CGH in other ways and test different imaging modes, such as magnification. So in this case, I moved the CGH axially, and the spacing of the image of the features on the CGH would change at the test surface. And then another thing I did was I clocked the CGH. So this is rotating it around and measuring that degree of freedom. And so these are some of the fringes that are the sort of the fingerprint of a Y translation. This is both of them moving the same way. This would be this moving out, and that way, and this way, and this way. So this is a pair of them. This is the two with plus or minus magnification. And then this would be plus rotation and minus rotation. And they change in a way that we can measure nicely. So now I'm going to talk about the apparatus I built and how it's similar to that other interferometer test that we described. So here's the source of it. This is a single mode fiber source, and that comes out to the condenser lens. And so without the CGH here, actually, this ray path looks very similar. It focuses the light here, because in this case, this is the test of the flat surface. So it focuses the light here, and then this is a plano-convex lens. So it basically, that front surface collimates the light, it then reflects off the flat, comes back through, and then the test plate focuses it again here. And there we have a little spatial filter and a lens to measure the interference. And one of the relevant things, you can kind of tell from the 1-inch grid on the table, but it's a 68 millimeter aperture with 695 samples across that full aperture. So the fabrication of these was done in a way where I basically made a big version of what I wanted in metal and then put a hole in it so that I could then change the height and have this tool, it's a spherical tool, ride in the big sphere and just barely touch down and carve out a portion of the optic that had the radius of curvature I wanted and the size I wanted. So here's these fine adjustment screws so I can change the height of this guide ring, and the polishing tool rides in here, and if it's lower, so if H is higher, that's basically determining the interference between the tool and the part, then I get a bigger feature. The diameter is related to H and also the radius of curvature. So these features are really shallow. I had to control it to about 5 microns to make this work, and so actually diagnosing what height it was something that I did to get that right. So now these are the results, and I'm comparing here the design. So this is what radius of curvature was assumed when I designed the CGH, and this is the radius of curvature that was actually measured after I made the features. And in general, if I have a tool radius of R, RF was a little bit longer. It was a little bit less curved when I made these. And I highly recommend, if you ever make these and design a CGH for them, to make the measured radius, or I'm sorry, to expect that the measured radius of what you make is going to be a little bit longer than your tool shape was. So in one case, 252, that was an empirically derived offset where I assumed it was going to be a little longer. This feature, and we call this sample 5, had a little bit higher radius, and these had a little bit lower. And so it kind of, some noise there. It wasn't perfectly repeatable what radius I got. But the features were nice and axisymmetric. They didn't have astigmatism or coma, at least not a dominant amount of it. And so that's good when we're measuring something that's not symmetric like tilt. So another thing that we wanted to do is understand where they were, or see how well we could measure where the features are. So here's feature 1, here's feature 2, relative to a set of mechanical data. So we used a setup where we had a microscope focus at the center of these 3 balls, and since these are also spheres, we can focus the microscope at the center of those and diagnose where all the different centers of curvature were. And so comparing where these 2 centers were, we could do that with about 1 micron random error. So that was very repeatable. Basically, the probe here was a really good diagnosis of where those centers were located. But to understand where the vertices of the features are, you have to, if this thing has a radius of curvature that's this long, let's say that's its center up here, you have to project down normal to the parent optic to understand where its vertex is. And the vertex is essentially the low spot. And that was a little bit more noisy. And it was about 55 microns, I'm calling it, for features with this radius of curvature. And you could improve that by diagnosing the angle of this better. And so this is when I only measured 3 points on the surface. You can measure more points and average it down. And so my measurements represent what happens before you boil it down to averaged out lower noise solution. Now, the experiments with one fiducial I demonstrate here with some ray traces. And again, here's the test with a flat, and we have a focus near the projection lens, and it relays back. For sample 2, it had a very short radius of curvature, so the intermediate focus is like right there. And then we have this tiny feature, also focus the light here. For sample 5, the intermediate focus is a bit further out here. But in both cases, they're filling the projection lens, and that's one of the limitations of how sensitive you can make these. If we made that feature larger in diameter, that beam footprint would vignette at that aperture. So for the 2 different samples, which vary in curvature and size, they were designed to be essentially the same sensitivity, but sample 5 was expected to have a higher dynamic range. So here's a picture of the setup with an indicator measuring translation to CGH, and this is the mounted sample. And it's notable that this is how I did the phase shifting, because this is a phase shifting interferometer. It's with a little piezo there. So that moves this back and forth by a very, very small amount. Now, this is the actual data, and if you're upset by this noisy stuff, it's because we didn't get an AR coating on the CGH. If you got an anti-reflection coating, then it would be a little bit nicer looking. But when I removed the CGH, none of those artifacts existed, so it's from those internal reflections. This, you can't even really see it. Right in there, it's only like 10 pixels is the interference pattern that's going to give us all the data that I'm going to show next. And maybe you can see a little better here because it's blue on one side and yellow on the other. That's the area that we observed the OPD from the smaller feature sample. And the rest of this is data. That's not just artistic shading. That's a measurement of, even though it looks chattery, we can unwrap the phase nicely and tell what the surface profile of the parent optic is at the same time. And that's important because we're trying to do an interferometer test where we test both the parent optic and check its alignment. So over here is sample 5, which is a bit larger, and you can actually see those tilt fringes, and that's the unwrapped phase. So now taking that and measuring the tilt, and that's what these are measurements of. The vertical axis is the peak to valley OPD, measuring the tilt in that interference pattern. We have superimposed horizontal and vertical shear, and it's expected to be the same sensitivity. These plots suggest that it is. These are linear regressions here, those lines, and these error bars represent the random, basically the noise in the OPD measurements. And this is the lateral displacement of the CGH. You can see from that it's plus or minus 80 microns where it stops, and we get a little bit of error here, but the full dynamic range is about 76 microns. And that actually is a bit more than was expected. But also it's starting to behave a little more poorly out there, so you might have been doing badly because of lack of sampling. Now for sample 5, it stays really well behaved through the entire dynamic range, and it matches what was expected. So 203 microns matches 204 microns. And here are what the fringes look like. So you can see we only have just a handful of pixels across here, but it still works. So that represents about the minimum number of pixels you'd want, and this is, you know, pretty nice. You can easily see these the variation from dark to light in those fringes. So I got some of the noise data here, where in both cases it was about plus or minus 30 microns, 2 sigma. So 2 sigma means we're 95% confidence that this number is correct. And that represents about a 20th of a wave, and that's a figure I mentioned before when I was talking about the performance of the other interferometer. And so I'm going to claim that my interferometer worked based on that, which is good, because it should have done about that well. And the sensitivity was within just a couple percent of what we expected from first order. So that's not even from the doing a fancy ray trace model. That's from all of my assumptions about this boiling down to a few numbers and simple algebra. So that's cool. And it's achieving about 1.5 microns in both cases. See, these numbers are a little lower because the sensitivity is a little higher experimentally in that case. So there's some other error sources which I didn't delve into too much or at all. But if we have power or coma in the surface, and that's the surface figure we made for the alignment references, then depending on where, in the case of power, what pixel we call the center of our measurement area, you can get a variation in what the tilt would be. And if you have coma and you change the size that you're measuring when, for example, you measure the location of the objects and then measure the alignment, that can contribute to error. So those have a little contribution. Actually, coma can be pretty bad. I made a conservative judgment there. But anyway, it's going to do about 2 to 3 microns for accuracy of where the CGH projection is compared to this set of, or compared to the feature. And then if we want to relate that to something outside, like to some chunk of metal in some other part of the room, then you can do that to 17 microns or 55 microns. The shorter radius of curvature enhances the coordinate measuring of that feature. In the case of two objects, so two alignment references, two fiducials, now we have these off-axis features here and here, and they're very similar to sample 5. They're about the same curvature and size. They're a little bit smaller because we have this limitation again at that aperture, and so I was forced to design this. This is design, by the way, not experiment yet. I was forced to design them smaller so that they would still work without clipping on the projection lens. And they're expected to have the same dynamic range as we had with sample 5. So before I was diagnosing the shear of the CGH, we already saw that as indicator on the side of it. Now I want to measure what the clocking is, so I have these two indicators separated by some distance that I measure, and I can do some simple trigonometry based on the difference in their readings and understand how it's clocking. And that's a separate measurement I need, so that I can say, oh, the interference says this clocking, and I have a mechanical diagnosis to corroborate that. So the other thing I measured was how much the CGH moved axially when I was changing the magnification of this. Now, here's the response from this test where it's aligned close to a null response. And here's the alignment features showing a nice null, and looks quite nice, I would say. You can see a little dark ring there indicating that there is some residual power in it. But these have a nice null, and you can align it so that it has a better null, but pretty low density fringes from the parent optic. And again, we can measure the optical path difference in all of them. So now I did the same thing to calibrate their shear. Same plots you saw before. Here's the noise and error bars, and here's the fringes indicating a misalignment in this sense and a misalignment in that sense of the projection. And the dynamic range is a little bit reduced, and I think that is from these being off-axis features as opposed to the on-axis feature. And also they may have clipped on the projection lens a little more easily on one side of the movement as a result of that. That's kind of my supposition, but if you're removing the test plate instead of the projection lens, you'd have less problem with vignetting on the projection lens. So, but I mean, these values for the dynamic range, it's not really reduced by that much compared to 204. And the idea is to design this so you're aligning it to 0 anyway, so having a huge dynamic range shouldn't be that vital. So, extra follow-up there. Now, these again have fairly accurate sensitivities. They're off by a little bit more, but here we're counting pixels to determine what the effective size of the feature is, so I think there may be some opportunity to get the wrong answer in that sense, because as we'll see in the next measurements, these measured sensitivities are quite accurate. They gave us accurate measurements of the clocking and magnification. Since the features are a little bit smaller and less sensitive, they have a higher uncertainty, but still about 2 microns. And the residual power is an issue when you're considering what's the total error that would be contributed here. It's more like 5 to 8 microns, or sorry, yeah, microns of alignment, and still about 55 for where this projection is in absolute space outside of the instrument. This plot demonstrates that we have, so this is clocking measurement residual. That's why we have this convenient dotted line at 0 that everything's following. So, with the exception of at the ends of the dynamic range, you have an accurate, so all the noise falls around the line defining accuracy for these measurements, and the full dynamic range is 0.7 degrees for detection of the clocking of the projection, and the noise is about plus or minus 0.005 degrees for 87 microradians, 18 arc seconds. And here's, again, the fringes that are related to this data. And this is the variation in magnification. So I measured the Z translation of the CGH, and this is, this black line is from my optical modeling what magnification the system should have if I were to move the CGH by such and such amount relative to 0, where the magnification was known at 1.61. So we were able to detect the magnification of the projection in the range from 1.593 to 1.634. And again, only at the very ends of what I consider the dynamic range here do you have any discrepancy between an accurate result and what we measured. And here we have the noise as 3 parts in 10,000 for the scale of our projection. So, in conclusion, the noise levels we achieved for aligning things, what the random error contribution is 1.5 and 2.2 microns, and that's just for these examples. So if you have an opportunity to design these with different parameters, you'll get different results, and you can push this farther, or you can even design the test to accommodate them better than, for example, the TAO test was designed for, because that was designed to use the cameras. So. There were small contributions from figure error here, partially because I was able to design the CGH to accommodate one of these samples, so that's a big help. And so that's what I want to highlight here. You want to align these to a null, and so if you know exactly what all the features are, and you make the CGH adapt to those, then you'll be able to say, oh, it's a perfect match of interference for everything. That's an alignment. So I would highly recommend that you build the sample first, put all the alignment features on your optic, then design the CGH, and then you get the optimum performance. So in conclusion, we had a successful implementation of an existing approach to alignment, which was HET, and this was, as Jim offered, it was really important to a lot of people, including me, and I couldn't be happier that it's on the sky actually doing something, because I like the applications of my work to be satisfying. And this is a couple views of it under test. And here we have an interferometer up here, and the mirror is visible here. This is pretty cool because you can see how curved M5 is. That mirror was a very aggressive aspheric mirror. It's difficult to make, difficult to test, and difficult to align. And so we have a really good success there. This is a picture of the Tokyo Atacama Observatory interferometer, and I credit the hardware implementation to Brian and Andrew, and also Matt Dubin, who did most of the implementation. I've been doing more system engineering side of that and using it as the poster child for my research. And the progress we have here in the field of making the alignment with the phase fiducials is we have a parametric design and performance analysis that's been verified with demonstrations, and my feeling is that this really needs to see an implementation now. Once you increase the scope like that, as with HET, you're going to come up with something that's, I think, really interesting, hopefully effective, and actually have your feet to the fire on whether or not it works well, and find what is really limiting about this or what's really great about it. So there's some further refinements. You can do a better job with the fabrication, testing where the features are, or what shape they are than I did, and possibly, depending on the interferometer, the noise level could decrease. But I don't think the noise is an issue in the first place. So this is, I think, the most interesting number we get out of this for the TAO alignment. This is really important, knowing where the projection is in an absolute sense, because you also need to measure the test mirror and align it to that. So I think that realistically we could do about that well. You know, round up a little bit if you want to be conservative, but be more, I guess, that's kind of the full story for this, versus with the cameras, there's even minor issues that were bigger than that value. So I hope that this will help chop down our tolerances on things and make better mirrors. I'd like to acknowledge, first of all, I've been very well funded throughout this, and I appreciate the heck out of that. And that's come from the HETDEX project for HET. So for all its difficulties, it was a good funding source, and I appreciate those guys. And the TAO project up to, basically rounding out my career here and motivating this research. Jim Burge and Dayluk are great group leaders, and I appreciate you guys being at the wheel to keep all this stuff going. And there's been a lot of collaborating staff, and I do want to name every one of them because Chengjian is a great supervisor. Brian is the man still down in the shop, and it's been great working with him. Andrew is a very talented engineer that I've gotten a lot from, and I really appreciate working with. Ping she's helped me with some code that produced a lot of what I've done here with fitting Zernike terms. Chen Yu did the CGH design for this, so that's really vital. Again, Matt worked with Andrew on TAO test, and he's just been consistently teaching me everything. Todd Horn is an interesting guy, but he taught me a lot of stuff, and I'm like a lot better with metal because of him, so I appreciate his contributions to the program too. Scott and Marco are really good with mechanics, and they support me a lot in HET. They're patient with me, learning how to interact with mechanical engineers. Vince, Bill, and Norm round out the optician squad, and they've all been great guys and taught me a lot. So Laura and Wen Xuan are also really notable. Laura I've interacted with a lot and followed up on her research, and I'm sure she's as happy as me to see that it worked out. And Wen Xuan, he was really interested in all the stuff I did, and he'd always come in and be complimentary but critical. And he gave me the phase unwrapping code that produced all this stuff, so he just kind of handed it to me on a platter. It was great. So, yeah, and then I've got all these references. So, I like to keep track of references. All right.
Questions for Eric?
I have some questions, Eric. When you are trying to align these 1 meter class mirrors into a structure, you need to have a structure that can support that level of alignment. I wonder if you have any trouble on say, setting the mirror and then finding out that it was drifting or having any problems with the optomechanics of defining the position of the mirrors.
That is an interesting one. I think the most horrifying moment mechanically for me, because there was one defining one, was after doing all that and getting all those results, or maybe around the same time. We did the full tilt and back, and we had a lot of coordinate measuring of where all these mirrors were, and did the before and after check of where all the mirrors were relative to each other, and there was definitely way above our uncertainty, like these things have moved by such and such amount because of the structure flexing, but it turns out that the structure itself was designed so that everything flexes so that static deflection doesn't throw the mirrors out of alignment. And it turns out that the system still performed perfectly well with that kind of consistent and designed proportions of movement from the analysis that they did. So there's a lot of movement there in that static deflection that was kind of scary to me, and I'm glad it didn't cause a problem on Sky. And also, Brian wrestled that thing into shape big time because there's all kinds of little things that come up with interferences and opportunities to break things that we needed to avoid, and loosening clamps on our differential adjusters, because that's how you get the precision, and then the clamp, the stability, and trying to get that to be loosened and tightened and repeatable, and so that we could actually dial everything in. It was, the mechanics are really interesting in that, and it's great that it's worked and that it got shipped on a truck and that it still works. So, yeah, a lot of scary there.
One comment is that it seems to me that this corrector was designed by some lens designers, with a really consulting degree of, I don't know, I'm just guessing. They didn't have an idea of the level of how difficult it would have been to align these things. And you got the job because no one wanted to get the job to do that difficult task, because it's not, it wasn't really, I mean, it wasn't very easy to find a way to do it. You guys did a wonderful job in putting together these mirrors aligned. But I can imagine the designers, okay, here is a design that will correct for this spherical aberration. You figure out how you put it together, and who wants to do this? Well, it was a very tough project.
Yeah. Like I said, they did continue to fund it. You know. That's good. Yeah, Jim probably knows more about that, but I don't know if it was how painful it was to swallow at the time that decision was made. I followed that decision, but anyway, it worked out.
So I have some comments and questions.
Okay.
So first of all, I mean, I think this is a great stuff, because finally you convinced me, I mean, say goodbye to the conventional amplitude fiducials and move to the phase fiducials.
I want to remark right now, he came up with phase fiducials.
But this is really good. So
that's a good term.
Your I mean, data and work just really convinced me. I mean, wow, this is really working and great stuff. And second, I think it was very well presented, because I was originally prepared very ambitious series of questions, and you let me just track them out, because you basically mentioned about it throughout your presentation. So, but I still have few survivors, I think. I'm lucky. So if you go to slide 9, could you go to slide 9 here?
Yes. Going back
Or actually
through
17,
time.
17, I'm sorry, 17 and.
Okay.
So this shows, I mean, it really aligned on axis. And it's exciting to see slide 18, next slides, I mean, it is working really nicely over that wide field of view. So could you talk about what was your kind of backup, or how did you justify if it is aligned on axis, it is going to work like this? Could you
so the way that we were able to justify this is by, I mean, we had all the other alignments supporting this. So you could get this result and have a lot of these mirrors out of whack, where one would be over here, one would be over there, over here and there, and one portion, like looking from one direction, you could say, oh, it's okay as long as we move this test CGH over here. Part of what supported this was that when we lined all this up, we had the interferometer on axis. That was a constraint. We had all the mirrors aligned by the independent constraint. And then we actually used the location of the computer-generated hologram as a compensator. That's legitimate to do because okay, so the computer-generated hologram there serves as a phase reference. In that case, it's serving as a phase reference for what the phase of the light looks like coming from the primary mirror. And then the interferometer is simulating, here's a nice image point. And so we're doing it in reverse in the lab, but that's what the CGH simulates. So if I move the CGH around, that's kind of like the primary mirror staying still and moving the whole secondary optics thing to receive that light from the right angle. So we have the freedom to do that, but if I had the mirrors all, here, kind of crazy like that, you would start to see, okay, well, we aligned this to compensate it, but it's way over here. That's not realistic given all of our other assumptions about how well everything is aligned. So this was all about finding a consistency between all the results. So we had a consistent result where the CGH was out of alignment by, let's say, I think it was maybe 200 microns. And that sounds big, but as far as moving this thing around, it's not very much. Or it might have been less. Anyway, it was off by some amount. And that was from all the simulations of, okay, if we simulate this test and have a bunch of simulated errors, and then simulate the alignment of this test with that as a compensator in the model, it tended to be out by, about that much. So we said, oh, well then there's a bunch of cases that we simulated where the whole thing works, where the CGH would also naturally be moved by a bit to compensate these effects in the test. So we did a lot of Monte Carlo analysis to support this, and really Pan-Shin supported that a lot in the project, simulating all these different cases and how the telescope performance would be if all these alignments didn't exist. And in the plot here, in the gray, this is generated from taking that kind of approach and saying, well, here's this possible statistical scenario where it's consistent with all the results, but the performance could be this bad if one of our assumptions was wrong or something. And so they were worried about one of our assumptions being wrong about the alignment of M4, because we had instabilities of other alignment references, and we said, but this one's stable. And then we proceeded. It was a big risk, but it worked because we didn't end up with that case that would be consistent with that assumption being wrong. So we didn't have the opportunity to see this at the time, so when we shipped it, we were hoping that we wouldn't see that.
So, thank you. If you go to slide 31, you mentioned about scaling up this thing for very large optics metrology. So in that case, usually you always have an air turbulence, and that will also affect this phase fiducial, interference fringes, which is mainly tilt. So did you consider that effect? This is my future story, of course, but have you ever thought about that? What if those tilt fringes are continuously moving around because of that air in the beam path?
I did not simulate that effect at all. So
okay.
That has not entered my air budget.
Maybe another students can do that in the future.
What do you think it would do, and how would you deal with it?
Well, one thing you could do is average it out, and there's other. Well, depending on what you're doing, it's so if the air turbulence is random, that would be my biggest recommendation, is taking a lot of measurements and averaging it out. And if you have some kind of instability, that's actually something where I think this projection measurement is pretty valuable, because if you say, we have this structure and it's going to hold the CGH projection aligned at this spot, and you assume that's correct, it'd be nice to have a direct measurement of it and see if it varies in time randomly or not. And so this actually, it gives you kind of a nice diagnosis of that. So, is that sufficient?
And the last technical question is slide 39. So you are making this fiducials, and so usually how long does it take? And also, if it's not, let's say, really easy to make it, did you consider making those fiducials as another CGH and just mount it on the surface?
I thought about that, and I thought about the idea of maybe having like a CGH sticker.
Right,
but
something like that.
I think the problem there would be making it accurate sticker. What would be the substrate for that, so it wouldn't stretch or something like that to make it inaccurate. That'd be one possible concern, I guess, for it. And I didn't end up trying it, and I figured this would work well. You could also diamond turn this if you had like a fast tool servo, especially. And actually somebody else has done that. So I found a kind of research where they had outside of the clear aperture some little features on the same substrate as a freeform, but it was a proceedings paper that didn't give like a general picture of how this design goes and everything. So that's another. That paper actually represents one other way you could make them. It's by diamond turning, and I also don't think they took the approach of independently testing the locations of everything and designing the CGH to that. Because with their tool, they have, with diamond turning machines, it's sort of an advantage that you can, without testing it, just have it make something. And so you can have the things exist, and the accuracy of the machine, legitimizes your knowledge of this is where these things are. So that's one other approach other than the sticker idea. But there's other ways you could print the CGH on there, I imagine, and onto something curved and have it located there. And it's not inherently problematic. It's possible you could do that.
And the last non-technical question is, I love your bicycle picture.
Oh.
So those two wheels are well aligned enough, and how long you can ride that? It's just, I just love that bicycle. It's one of a kind. So
I'm glad you like it. It was not aligned very well. No, the wheels are well aligned. The frame.
I thought your spoke is CGH pattern there. So no, I'm kidding. But
it's a little bit of a decompression from alignment, doing stuff like that.
okay.
So I had a question. You showed images of the interferometric measurement with the fiducials in there. Could you go to that slide? I think it's a few further.
That a couple times. Let's find one of them.
Yeah, that's a good one.
That one?
So the where the fiducial is, there's an outer ring. Can you explain where that comes from?
Yes. So it's hard to control the height of the guide ring when I'm trying to make a feature of a certain size to a tolerance where I am going to not have an excessively large fiducial. So this is extra space where the curvature is distinct from what is otherwise flat out here that I don't need, but it came along with my lack of ability to control the height of the guide ring to any finer of a resolution. It was a fairly dynamic challenge because I actually waxed the guide ring on, so I was heating it up with a heat gun, melting wax, cooling it down, and then measuring the drop from the guide ring to the center with a spherometer with a separate measurement that I was offsetting from where I took the spherometer off center and measured the guide ring itself. So I said, okay, that's the sag from 3 outer supporting points to the sphere. This should be different by this amount, and went by that. So what I didn't want to end up with was too small of a feature, and it does have some edge roll off. So there's an affected area and there's an effective useful diameter. There's 2 different things. When I make an interferometer measurement of the surface, I have an inner area and I say, okay, that area is all a good sphere. And then when I make a measurement of the flat like this, you can see, oh, it bends down and then the fringes become so dense I can't see them. There's kind of a dead zone in between that's outside of either measurement's dynamic range. That, and out to where it finally rolls up to a nice flat. I call that full diameter an affected area. And I mentioned that in the dissertation, give some figures for how big the affected diameters are relative to the useful diameter. So you can see how much this method wastes, basically, of surface area. Because you could make it so that the useful area, if you did a better job controlling the guide ring, you can make it so the useful area matched what you wanted, but you'd still have some larger affected area using this way of polishing them.
Yeah, thanks.
I think for the TAO secondary, there were 2 distinct CGH plates for the zones of the UUT.
Yes.
Was that like part of why was 2 necessary? Was that part of the trade-off of sensitivity?
Okay, I actually have a backup slide that's going to come in handy because I was afraid how long this was becoming. So let's look at this slide. So this slide shows the actual design of the interferometer, and we have here this is the cartoon portion. I'm showing it testing the inner area. So here's the center of what it's testing, and that's the edge of the testing aperture. We saw that picture of it actually over the glass, but this is the pattern, and this is something Chen Yu described as design input for me working with this design. Of this is where an inner portion is tested, and this is where an outer portion is tested. And you can see there's a significant amount of overlap, and that helps you relate the different measurements to each other to stitch everything together. And what you don't want to have is like every one of those be in an arbitrary place in a grid, because then you'd have to make that many CGHs, and we don't want to do that. So instead, we make an inner ring and an outer ring, and then you align the interferometer to a certain offset from rotation, and then you rotate it around, and you keep the interferometer stable, or like in the same place, relative to the rotation axis, and just rotate around and measure, and then move it outer, or out some, and then do that again. So in that way, we only need 2 CGHs.
Other questions? So I have a question for you.
Yes.
What next?
So next, I'm going to, more directly next, I'm going to work on developing a publication from the data for the phase fiducials, and then just after that, I'm going to Colorado, and I'm going to work at Ball Aerospace, and I'm happy to have a job. So.
Great. Well, thanks. So this concludes our public presentation of Eric's dissertation. Thanks for coming.